guys, this is Shelby with the Rogers Public Library. So this week for Full Steam Ahead, I want to talk to you guys about gravity. So you're probably already familiar with gravity already, right? That's the force that keeps us on Earth and it makes objects fall down, like apples. It's also the force that makes the Earth orbit around the sun, right? So, but I want to talk to you about gravity in a little bit more depth and about Albert Einstein's ideas of gravity. But to do that, we need to talk about someone else first, and that's Isaac Newton, right? I printed a picture out of him because I think his hair is really silly. But Isaac Newton, he was an English scientist in the 17th century, and he didn't discover gravity, right? Because people have known gravity for a really, really long time. But he did do two very important things. And the first he said, well, that what I've already told you, which is that the same force that pulls us towards the Earth is what makes planets orbit around stars and moons orbit around planets, right? So it's a universal force. And because it's a universal force, we can use laws of gravity and laws of motion to describe movement, not just on Earth, but in the entire universe, right? And in making these laws of motion, he came up with a new type of math that describes motion really well, and that's called calculus. And we can think of that as the math of changing things or things that change over time, right? And there's actually a little bit of controversy here because Newton wasn't exactly the only one that came up with this idea. There's this guy with even sillier here, Gottfried Wilhelm Leibniz. He's a German mathematician who also came up with a lot of the same ideas about calculus that Newton did. The difference is that Newton applied these ideas to science and to physics in particular, whereas Leibniz was more interested in just the math part. So, but Newton's laws of gravity, they're really good. They describe how a lot of things in the universe move, but they're not perfect, right? So in the 19th century, Mercury was acting weird. And the way that it was moving didn't match up with the way that Isaac Newton said it should move. And so people were really confused. And Albert Einstein came along and he said, well, maybe there's more to this gravity thing, right? And his theory of gravity is called general relativity. And general relativity starts off with something called the equivalence principle, right? And the equivalence principle is all about inertial frames of reference. And an inertial frame of reference is just any situation where you're sitting still relative to your surroundings, right? So right now I'm in an inertial frame of reference because I'm not moving relative to the chair and to the table, even though we know that the whole planet is actually moving through space really fast. I don't perceive motion on a local scale, right? And there's actually a cool experiment we can do with this. We have a cup, and we're going to put some water in it. So, right, the water gets pulled, it falls out of the cup because of gravity. But let's watch this. What if we drop the cup? Do you guys think that the water is gonna fall out while it's falling, or do you think it's gonna the whole thing's gonna fall at once? Woo, okay. So that was a little bit more messy than I intended. But what we should have seen was that as the cup falls, no water comes out of the hole because the water and the cup are attracted to gravity, are attracted to the Earth at an equal rate. They're affected by gravity equally, so they don't move relative to one another. And so we'd say that the cup is in an inertial frame of reference. It's not moving in relation to its surroundings. And this is kind of the basis for the equivalence principle. But there's one other part of that that's a little bit more complicated, and so I made a diagram, right? So this, basically, if we have a box, it doesn't have any windows or doors or anything, and it's just sitting on the Earth. Inside the box, you'll feel gravity pulling on you, right? You'll get attracted to the Earth the same way that the cup and the water got attracted to Earth. But, and we can quantify the pull of gravity, right? We can say that things that fall accelerate at a rate of 9.8 meters per second squared. That's Newton's law of gravity. But what if the box starts moving upwards, right? What if you start accelerating upwards at the same rate of gravity? Well, there's no doors and there's no windows, so you would have no way of knowing if you were sitting still, if you were moving. It would feel exactly the same. So, you know, now you're in this box and you're really bored because there's no doors, no windows, you don't know what's going on. So you throw a tennis ball at the opposite wall. Well, the tennis ball doesn't move instantaneously. it takes a little bit of time for it to hit the opposite wall. And in that time, the box is going to be moving upwards. And so by the time that it hits the opposite wall, it's not going to hit straight across in a straight line. It's going to hit further down. It's going to curve. All right, so what if instead of using a tennis ball, we did the same thing with a flashlight? We know that the light moves really, really fast, but it has a finite speed. It doesn't move instantaneously. So in the amount of time that the flashlight takes to travel across the box is going to move up a little bit, and the beam from the flashlight is going to curve. It's not going to curve as much as a tennis ball curves because it moves a lot faster, but it's going to curve a little bit. Now, this is weird, right? Because when we think about gravity, we think about the attraction between things with mass, right? Between really big objects like the sun and the earth and the stars, right? But light doesn't have mass. Light is made out of photons, and photons are massless particles. So if that means that gravity can't just be the attraction between things with mass. There has to be something else to it. So Einstein thought about this a lot, and what he said was that gravity is actually an illusion of force. What we actually experience when we're experiencing gravity is the curvature of space-time, right? And this is the part of general relativity that's really complicated and really hard to understand. Because first, what does space-time even mean? Well, the way that our brains work is we're used to thinking of space and time as being separate things, right? Because we can go left and we can go right, and we can go forward and we can go back, and we can go up and we can go down. But we can only ever move forward in time, right? It's different than space. But Einstein said, no, it's not. It's really the same thing. And gravity affects both space and time together. So that's part of what makes general relativity complicated. The other part is that you need to know a lot of calculus and a lot of geometry, a lot more than I can explain in just a couple of minutes to really understand all the math that's going on. But there's something that's easier to understand than the curvature of space-time, and that's the curvature of space. So as an example, this is a sphere, right? It's the Earth. It's just a globe. And so when we're looking at this, we can see there are lines on here, right? These are called longitudinal lines, and then these are latitudinal lines, right? Like the equator. So if you walked along the equator all the way along the circumference of the Earth, and got back, this entire time, you'll feel like you're traveling in a straight line, right? You'll put one foot in front of the other and keep walking, and eventually you come back to where you started. So really, you haven't walked in a straight line at all. You've walked in a curved line, in a geodesic. That's what they're called. In curved space, we have geodesics instead of lines. And that's the way that space-time is, according to Einstein. And that's the reason that the moon circles the Earth instead of just flying off in outer space. What it experiences is the same thing we experience walking along the Earth. It feels like it's going straight, but because there's a bunch of mass concentrated in the Earth, that straight line gets bendy and curved and kind of spherical. And so this straight line turns into a circle pretty much. It just goes around and around instead of going off out into the middle of nowhere. But yeah, so that's gravity. I hope I explained it to you guys well. This is really complicated, and there's a lot of stuff that scientists still don't know about gravity now. So, but if there's more questions that you have about it, you can go online. There's a lot of really good resources that you can find about gravity. But for now, we're going to move on to our craft. For this craft, what we're doing is we're making things called lissajous figures. So lissajous figures are a type of complex harmonic motion. And what that means, when we talk about harmonic motion, that's usually like waves, right? So something that just swings back and forth. But the way that this is a type of pendulum called the Blackburn pendulum. When it swings back and forth this way along one axis, the length that it swings is longer than it is when it swings side to side. And so it creates really, really funky shapes. What this is actually made out of is the top of a half gallon of milk that I hot glued a funnel onto. And then there's just a rope system and some binder clips up top that are holding it up. I actually refined my design a little bit better. So this is the top of a water bottle with a little hole poked in the top. I'm just held up by a fishing string. So these are a lot easier to make than this one is, but it's the same principle. You have a pendulum connected to a string connected at 2 points so that it'll swing with 2 different amplitudes is what it's called. So we're going to put some sand in here. I'm going to cover the bottom. You don't need a lot of sand. And we're just going to see the patterns that it makes, right? Yeah, so it's making this really kind of funky, I don't even know what to call it. It's a wave, is the best way to describe it. Because we didn't put a lot of sand in it, it's already done. But here, and the actual pattern that it makes is determined mathematically by the ratio of this length to this length, right? I think it's called a sine, but S-I-N-E. But we adjust the lengths, we pull this up a little bit, and get a second piece of paper, we can make a new pattern instead. Yeah, so if you don't have sand, you can also do this with paint, but I imagine it's more messy because it's harder to clean up. But so yeah, we've adjusted this. We made this length a little bit shorter, so we should get a new pattern now. Yeah, that one's pretty different. You can see kind of the same basic structure, but the longer it goes on, the more different it ends up from the other one. And at this point, once you get a good coating of sand, you want to stop it and just get this rest of the sand off. Otherwise, it'll pull up in the middle and it will mess up your pretty harmonic motion. So that's our craft for today. I hope you guys had fun, and I'll see you next week. Bye.